I cannot believe it has been a year and a half since I've done a teacher tutorial walkthrough. We are now getting to the end of the WHIMC grant. This is our last summer of data collection. We've been fortunate enough to be able to dovetail it into some other projects, including the Invite Institute, as well as what we're referring to as Quick Red Fox or QRF. So it's still pretty relevant that we have these walkthroughs for people that are picking up and using WHIMC as we try to set our community partners in a position where they can continue programming. So once again, to review what these are about is just walking people through how the levels have been designed, what we're expecting learners to get out of a given environment. The walkthrough sort of includes both the single player version where you're playing remote from home, as well as a lot of the stuff that we hit when we run a camp where we've got like classes of kids all doing the same thing at the same time. So I'm going to go through our exoplanets and take a look at Mars, as well as some cool celestial bodies maps that we've added. So once students have gone through the 3 basic what-if missions, as well as the Minoa extension and 2 Moons extension, they should be granted the ability to go upstairs with this elevator to floor 2. I believe that's the Explorer status. And there's a bunch of different worlds up here. Notably, they're confronted by Mars as one of the first ones. And we're going to return back to that. There is sort of a you can explore it kind of Mars that's up here. And I'll also point out this one that we never really totally finished. You can still see it. It's cool. There's just no like quest infrastructure or framework to it. What I often do during camps or times I'm showing it off is just fly through it and ask kids if they know where they are. And we have some sort of preliminary measurements, but part of the challenges on it is it's like the exoplanets where like we have no real data on this, and we'll know more like when Europa Clipper gets there in 2026. But the upper floor of the space station is pretty neat. There's like this biolab where they're growing different crops in different conditions. They have the Mars rover simulation area. And there's a material sciences section. We had planned to do this asteroid mining thing. We would love if somebody watching this wants to build us an asteroid mining map. It's super cool. But the main thing that they would be going through in a camp, or that if they were exploring through, is the exoplanet lab. Now, once again, we have a PBS Nova lab. It's sort of well advertised here, and like you can like click on this head, and for instance, it will give you the link to go there. And this is that offline, or rather not on the learning environment in a browser. You have to be online. Way to learn about how we detect exoplanets through a number of different scientists that worked with PBS Nova. But the neat thing about this is that we also have built several exoplanets that are ones that are like real planets that we've discovered in real life, and we've tried to make simulations of them based on the most current data that we have. And so students can go through and visit some of these. And there's even this bonus world here. That was the winner of the exoplanet design competition. We had a student who made one. And some of these are pretty neat. Like Theron, who's a real life scientist, actually discovered the brown dwarf that he helped us design for this game. So anyway, that one is last. We're going to go ahead and I usually start them with Trappist. That's our typical start point. For a world, but when we're doing a camp, it doesn't really matter when they're playing through the single player version. They're given a quest, and I think it's like Exoplanet Tour or something like that. That's like given to them after they complete the next series, and it just said the quest is just to go visit each of these worlds, and the worlds inside of them independently will also have quests. So I've pulled up the teacher guide over here, and I'm going to go take a look at this. Once again, all of these worlds have teacher guides associated with them, the questions to sort of help assess what students have learned on them, as well as some of the observable concepts and anticipated questions. So we're going to talk about those a little bit. But if I fly over here to Trappist, they pop out of a rocket like they do in a lot of worlds. And this one is most strikingly full of an orange sky. And the world is this crazy, cool looking, like sort of brown, dead, it doesn't look very alive. And if they walk up to the astrochemists here, they're going to be given this quest, which is that they need to go find these pools of water. And let's see if I have one of the maps on me. I have BarrelBot instructions. I have something from another thing we're working on. But anyway, I can look at it on this map. There's basically these 2 pools of water. Here you can see one there, and then there's should be one in another spot nearby. And they can meander over to those to take some measurements. So I'm going to go ahead and do that. And as they're walking through the world, there's one of the things they're going to most obviously do is type /atmosphere, because look at that crazy atmosphere. And we did have a real scientist on the team, or a graduate student scientist in training, figure out like what would be the color of the atmosphere for this. And they can check other stuff like tilt and rotational period and sort of, I have to type it right. There we go. They have to compare it to, they can compare it to different conditions that you might find in Earth. But if I walk over here, I should be able to find, among all the sort of unusual alien environment, which is pretty wacky. I mean, just this is a what if we could go to another planet outside of our solar system. It's a crazy good prompt. Anyway, this is supposed to be like science equipment that is measuring this thing, and they can jump in the water. Now, I am an operator on the server, so I don't get hurt by this, but the kids will take damage gently. They'll heal faster than they actually absorb the damage. But if I do /composition, or /atmosphere also works in this, it will tell us high concentrations of chloride, sodium, and sulfide. And I've now completed that quest because I did 2 atmospheric measures. And you can actually do the other one in the other pool, and it's on the other side. And I guess I'll leave that mystery for you to discover, for the kids to discover. But that's the sort of most notable stuff. The exoplanets are not that big and involved, and part of the idea is to convey that they aren't very habitable. You know, if I type things like oxygen, it's going to say, well, likely none, but we don't know yet. Or, you know, let's see if there's any atmospheric pressure. Okay, so it's, you know, 1/10 of the pressure of Earth based on what we think we know. And again, we're looking at these things that are like many, many light years away through telescopes. Our knowledge on them every year changes. The stuff that, some of the notable things, a year is only 6 days. There's a lot of cosmic radiation, or I'm sorry, there's a lack of cosmic radiation because it has a thick atmosphere relative. And what else are on here? Orange sky, acid pools, geological formations, relative planet size, all things students can notice as they're running around and doing this. So that's sort of the first exoplanet that they can visit. This one I don't believe has any gravity modification. So then we'll go to another one. I'm just going to teleport to it, Cancri. And this one dates back to the beginning of the grant where we just had a simple like planet covered in lava was our whole concept. But this one is now, we've dolled it up a little bit more. There's these particle effects going on. They have a quest here where they can try to program this satellite. So here we have /radiation. And the idea of a lot of the exoplanets is to point out some of these characteristics that they haven't explored, these science variables they haven't explored yet on the what if Earths. And it's 600 millisieverts per year. I should be able to type that into this. Here we go. Oh, typical radiation exposure. I think I did. Yeah, it's 250. Let's try that again. 250. There we go. So it's asking me how much more radiation is there, and we're programming this thing to measure relative to that. Now, this is a pretty short and easy. They just see the world's covered in lava. They get that there's a lot of radiation. But if we go through the door here, this is kind of fun. It will actually take them over to the other side of Cancri. This map was made by Bryce, one of our same grad student who figured out the atmospheric colors. This is the quote-unquote dark side of Cancri. Remember, the other side was totally covered in lava. And they come out here and they get this cool view of like, okay, a steamy, crazy surface, and there's something going on in the sky. We can see the little hint there of the teleport up to the clouds above. And they're in a research base. So we have Cloud Lab on Cancri 55E. And they're trying to do different things here. There's like some fun computer station looking stuff. We also had an undergrad, Chase, who helped us out at University of Maine in making this. But there's stuff for like fabrication and research at this base. And there's this kind of fun drone launch. They'll shoot that off and a drone will go up. And that's part of how we know like how we're going to get measurements on our planet. And I believe if we talk to somebody, yeah, we talked to Sage. That's what the last thing told us. Here we go. So we can launch the survey drone. I think I might have already done that. I'm going to go do it again. But I think you talk to Sage and then you launch the survey drone. There we go. Okay. And I'm going to go outside. Now we, of course, are still wearing our spacesuit from before. Let's just get our hand out there. The gravity on this one is very high. So again, I'm an op, so I can just jump around and fly and stuff. But the students will have to go up these little half steps because they actually won't be able to jump a full block. And if you hit, yeah, we don't see it now, but if I hit E, you would see the effects of some of these things. But I can go like down these like short little steps. There's some people out here to talk to. We have scientist Kobe. And we can also do some obvious stuff like temperature. So the temperature is very hot. It's even hotter on the other side. So they can observe some of this stuff. But the crazier, cooler things is that there's these clouds up in the sky, these silicon clouds. And you can see there's the drone that we had launched like a minute ago. And if I go over here, it should take me up to the viewpoint of the drone. And when the kids are running this in a camp, I often will give them the challenge of, okay, who can find the drone and fly up in the sky? And we can go up here and type /atmosphere, and this will tell us another notable thing. It's primarily hydrogen and silicon. So that's the situation there. Wonder... Oh, I get down by jumping off the drone. That's right. Okay. So you can walk around the surface. They have some other scientific measurement tools out there that are pretty cool to see. They're obviously going to type stuff like gravity because they're going to be annoyed by the gravity. Let me go check my teacher guide here to see what else we would note on Cancri. As usual, these have questions attached to them. So let's see. Cancri is... why is one side of Cancri covered in lava and the other side is covered with the rocky surface? And this is because we have a tidally locked planet, which they can measure. But we've got radiation, temperature, atmospheric gravity, pressure, radius, and then these big thermal vents that are spitting up the material that's becoming the clouds in the sky, that silicon combination. Those are all different things that they might observe about this world. So this one's pretty cool. We're going to go to the next one. Let's do MVTP Kepler. Now, Kepler is probably the least realistic in our rendering because we made plant life. And the chances are Kepler does not have plant life like this. But it's neat to imagine that you have a star that has created a different kind of photosynthesis reaction where plants are reflecting back red light instead of green light. And so they can learn about this and sort of see this cool forest of just really unusual looking stuff. And also look at these mountains in the background. This was made with World Edit and World Painter by Eric, one of our undergrads, who made this really cool realistic terrain. There were big plans for this one when it was originally made because there's obviously this giant base here. The mission is really they don't have to go into the base. They're just going to talk to the scientists at the front. And we did actually block off the rest of the base because what we found is the students would be in line towards the base and just only be obsessed with that when what we really wanted them to do is explore the rest of the world. At some point, maybe we'll be able to expand this to do more. And this is part of why we've open sourced everything, is that if you want to make Kepler into a really cool mission world full of lots of stuff, that's great. So here we have a prompt for the water. You can jump in and try /composition. Nope, not compact. Composition. There we go. I can type, I swear. So we have 70% nitrogen and 12% unknown, 18% oxygen. And I'm just going to teleport over. There's a robot in the forest somewhere around here. Let's see, I find him. There he is. That's the robot. So that's another challenge I'll give students to say, can you find the robot in the forest? And they search around and they'll be making measures. But we have our robot chemist, not alchemist. And I should be able to find out there's a button on the side. Let's see if I can do this. Oh, I'm getting blocked by the plants. How annoying. I have to go around the long way. There we go. Okay. I do that, and I get some crimson roots, and we can bring these back to the scientist for analysis. I think I probably missed... I think I get the quest. I'm pretty sure I get it right here. So, yeah, there's the quest. I've got the roots, and now I can then go return these over to our scientist in here for analysis, who will tell us some about why they are the color red. Let's see if I can do that. Interesting life. I think I did the quest in the wrong order, so it's not giving me the result that I want. But anyway, if you do it in the right order, it should work. But lots of stuff to observe on this one. We've got the cool sky. The plants obviously have different colors. It's a chance for us to learn and think a little bit about biology. Let's see, other observable concepts. So we got atmosphere, year, gravity, radius, temperature, and then obviously the lack of animals, the water tint. It's kind of like an interesting question of can you have plant life like this without insects or animals or other forms? And would this even be carbon-based plant life as we know it? Maybe it's evolved with a totally different, chemical structure or molecular structure. Okay, now we go to the gas giants, and those are neat in a lot of ways because the students get a game mode that they don't normally get. So I'm going to go MVTP Glais. Here we go. And we've added this little thing up front. Oops. Get rid of that. Okay. And this helps explain, if I back up a little bit, you can kind of see, here we have our infrared view of Glais, and it's flying like a comet. So the solar winds are stripping away the atmosphere of the planet as it flies along. So, and that's been happening for a long period of time. it leaves this the sort of trail as the planet loses its mass as it goes. And you can kind of see the star lights it from the one side. You have a trail. And if we talk to Eric here, he kind of explains this. There's a YouTube video explaining how this works. But when they walk out back here, they have a couple of things. One, they can do a program probe. So we're emphasizing gravity in this case. So let's do a /gravity. Okay, so it is 1.18 times. So let's see if that works. 1.18. There we go. We can program the probe to be able to adjust itself based on the gravity. Now, in their case, they're going to switch over to spectator mode when they walk off the back of this, and they'll be able to fly around this planet. And this is making the point that gas giants, it wouldn't look quite like this. This is as close as we think we can get in Minecraft, where it's sort of this haze where it gets light and thickens up. And gas giants sort of get to be this like molten liquid format as you go deeper into them. But we have this glass that's representing the different layers of clouds. It's swirling. It's very active. Obviously, they fly down here in just a few blocks. This would be like orders of magnitude more distance. But what they're finding at the bottom is what the kids will say is ice on fire. And really, we're explaining that it's not quite ice on fire. It's a sublimation process. There's so much gravity that you have the water is pressured into a solid form. So I should be able to check pressure. That's atmospheric pressure. Hold on. Maybe, do I get a different measure down here? It's not showing us the right measure. All right, so I need to adjust that. But the idea is that like there isn't a lot of pressure because the atmosphere is actually very broad if you were or very thin if you were in the outer parts of it. But if you went down to the core, it would actually get very high. So I need to make a mental note here to have this scale be a scalable variable. But that's why the ice is on fire. And if you have fire in a vacuum, it's a spherical shape. It doesn't have the shape cut like this. But we at least make it as close as we can get. And it's cool for kids to sort of imagine what it would be like to visit a gas giant, how this would look like flying over this giant thing. And zipping around in spectator mode is a lot of fun. Obviously, for others, hardcore science folks, a spaceship like this would be absolutely crushed and destroyed in a scenario like this. So, obviously this also is not an interstellar capable looking. This is very sci-fi, to be able to visit this in all the different ways. But we're going to go to brown dwarf next. So this one was discovered by Theron, and there's a quest here. Let's go over to this. I can tap on the computer, and it's going to tell us, like, go check this thing out. We're trying to figure out what it is. And the question is this a brown dwarf? And brown dwarfs are somewhere between, like, Jupiter and a sun. So very large gas giants that are sometimes called failed stars. And we can type things like /atmosphere, and it will give us some atmospheric information. Good work. These readings match what we thought. This object is a brown dwarf. Do we have any more on this? Yeah, I think we get different readings. It should give us some other... let's see here. There are several planets in the habitable zone. Oh, that's the wrong. It's telling me all about the completed... Oh, here. It's look at the white text. We're seeing the completed text of some previous quests in here. There's a oxygen ratio of 1 to 5 for travel further to see more. It gets like really dark, which is kind of cool because the gas is really thick. But then eventually it lightens up again. And you get this effect where you get to the inner core of the planet where it's sort of like almost like a sun, but it's just glowing faintly. It's not a full fusion effect like that we would see with a sun. And I believe we get different atmosphere measures even deeper. Oh no, that's just their same 1 to 5 ratio. So you have to go into the planet to get that. Other things that we might care about with the brown dwarf. Let's see. I mean, obviously that purple sky. They get to learn a little bit about what is the difference between Jupiter and a sun. So we have atmosphere, temperature, year, rotational period, radiation, and gravity. Gravity is really crazy, unsurprisingly. And probably some other things we can measure in there too. So pretty interesting stuff with all those exoplanets. What I generally think of those as is that you can run all 5 of them in about the same length as you run one What If world. Maybe a little bit longer. What we often find is in a camp, the kids are sort of like they're ready to do new things. And the activity that we tie with this is we actually have them draw an exoplanet. So they learn about real life exoplanets. We have a slideshow to go with this. And in fact, here I can share that. Okay, so here are the exoplanet slides that would be a follow-up. So it's this question of what if we could visit exoplanets. We ask about this question of if Earth is special, if we could find other planets that are like it, and really there's a planet or more around every single star in the sky, so there's tons of planets out there. Reminder that they can think about that it's hard to see some of them due to lighting and size and all this other stuff. They can learn about how we find them with the exoplanet lab. In previous camps, sometimes we've had the kids actually do the lab, but typically kids are in a camp because they want to be together. And so this works great if you're like playing at home and you want to play like through this alone. But when kids are in a room together, they're less excited. There's also a good chance to remind them about science tools and observations. At this point, they often need a reminder of that. And the science tools are really worth using on these planets because they're unusual. And they can do, if you don't want to do the quests in the game, because kids often won't read the text while we're playing, so you can put this up on the screen and say, all right, can you find ice on fire? What does the tail on Glaius remind you of? There's sort of questions to give them thinking about it. And then we review the planets. So Trappist, we explain why Trappist is named like it is. So it's the name of the star, actually. It's not the name of the planet. And the name of the planet is sort of the 1E. So we explain how we find these things, categorize them, and how the knowledge is changing in them all the time. And that the water on Trappist, even though it is in the Goldilocks zone to have liquid water, it still doesn't mean it's habitable water for humans. It would be like the water in Yellowstone where it would kill you in our scenario. It may not really be like that. Kepler, same idea here, where you can collect a sample to learn about how the plant life has turned out differently. Cancri. And then you can pause if you want and make comparisons of like which of these planets are more habitable, and you can have a debate between the students about that. The answer is none of them are habitable, but how uninhabitable are they is a kind of fun question. So Cancri is totally covered in lava. We can review what eyeball planets are like. That picture is not great, but it does kind of convey this concept of it's half and half at least. And we talk about how the magma, you can have different elements in your melting rock that can create for different systems of atmosphere, including clouds made of silicon that are reflective. And then Glaius here, the giant gas giant, once again explaining how it's losing its atmosphere and how fire works in a vacuum. And then brown dwarf here is giving us some relative size and how it's a failed star, and Theron has discovered this one and many others. And we can ask that habitable question again. Okay, and then there's the prompt for drawing your own exoplanet. So once the kids have visited exoplanets, they can come up with their own. It's fun to imagine what would another planet be like. But this is, besides the chance for them to apply their knowledge of the science variables at the bottom in drawing something, it's helpful for kids who don't like to write. Often kids like to draw more than writing, so it's a different way to express. And I actually think it's as important. We express ourselves visually so often. And we should learn more skills. But I get really into this idea that they should label things, visual annotation, if we're going to be professional about it. And so they can draw a planet, but then they label stuff about it, explaining these science concepts. And by labeling them, it shows their knowledge of it. And also you can have conversations about how to clarify if you wanted to do this as like an assignment or something. They also don't have to do just the planet view. They could be thinking about its neighborhood. Like I'll have a lot of kids draw a circle and be like, okay, I'm done. And I try to prompt them a little more to like think about what else could they draw? How can they label things? But you can also say, does it have moons? Is it in a solar system? How do other planets affect it in that setting? And then they could also do cutaway diagrams as a fun way to like think about the inside of the planet. What's it made of? And that gets into this discussion about tectonic behavior and our magnetic field and whether or not we would have one if the planet was just made of diamonds, for instance, which is a common thing kids will say in Minecraft astronomy camp. And then you can also think about the view from the surface of the planet. Like this is a picture from Venus, which is totally crazy that we sent down a probe that got crushed and destroyed by the extreme conditions of Venus. Their planet might do things like that. So that is the presentation for exoplanets. What I want to do now, and I'll just switch over to the other PowerPoint. Here we go. We were lucky enough that Christopher Slayton, who's I think he's 20 now, living out in California, a fairly famous YouTuber, made Minecraft, the Minecraft universe, the universe in Minecraft. And his take on that was sort of these celestial scale formations. He's really talented, made some cool stuff. There's also a JWST map, which is, if you want to talk about like Hubble or JWST, how we find these exoplanets and see these faraway galaxies, it's fun to visit that. And again, we can fly through these worlds. While they don't have scripted quests attached to them, it's still a good opportunity for students to fly through and look. When we do this camp at the planetarium, we'll often visit these worlds on the planetarium dome, and they look really impressive. So I already pointed out extraterrestrial life earlier in the video. That's the shrinking down, what it might look like at the bottom of Europa if you were shrunk down really small. Microbial life that lives around heat vents down deep down in a place like Europa. Here's a Europa Clipper imagery. You can visit that one. We also have a black hole. So kids always want to visit a black hole. I should say we have like 3 black holes actually, but explaining what is the anatomy of a black hole, the different components of it is a fun thing to go with it. Here we have Sagittarius, the center of the Milky Way galaxy. That's a map that's on there too. We even have some pictures of this one that we can talk about. Here's our quasar, a black hole absorbing all kinds of stuff nearby. Explaining what these kids always ask, like, what are these beams of light coming out of the quasar? What's going on with that? Explaining those is one piece, part of the particle projection, and we can see those from really far away. Supercluster is one of my favorites to show off this idea that we have many galaxies and that they're eventually all going to collide with each other or merge in different ways. Just seeing sort of this galactic scale. And on any of these maps, we actually have a variable called scale, where they can then check their block size relative to the place that they are. And we can talk about supercluster groups in the bigger way, and this idea of the Milky Way merging with Andromeda in a long time from now. Pillars of Creation, another favorite, really iconic looking. You can show the picture of how this looks through infrared versus through Hubble. Neutron Star, it's another one where it's a pretty neat map. All of these, if you were going to run them in a classroom setting, I would treat them like the exoplanets where you're flying through them quickly and then you're explaining them with a PowerPoint or the slideshow before or after. I try to not do too much talking as a ratio of talk to explore. Sometimes we don't do this presentation and they just go through and ask questions. There are a variety of ways you can do this. And you land on the universe, which is this really crazy cool one that Chris put together of our best understanding of this model of, like, you can kind of see how the outer edges of the way it gets to it be rendered like a spider web. We can explain what we know about how we talk about the universe. And there are actually more than just these. So if you download we have an instance for instructors that has some of Chris's new maps, which actually includes one, for instance, that's called Solar Giants, which has effectively Gliese. You have a planet. In fact, I'll just show that. So these are best done in single player because they have a world height that is higher than what you can do easily. There's a bunch of mods that you need, so it's best to do it by downloading the instance. But there's even more ones, so you can see infinite Earths. There's sort of what if questions of, like, what if Earth had a ring or a totally different atmosphere? White hole rendering, Super Saturn with like many rings. Cosmic Forest is like these kind of ideas of how time works. So there's a whole bunch of these built in. Some of the ones I had already talked about. Let's go look at Solar Giants, because often there's not that much time to show all these. And so I'm just going to show a little bit of one. But here we go. Now, I've got my view distance up to 32 right now. You need to hack it to go even bigger for some of these to work effectively. But we have sort of this giant sun, and it looks very different color, right? And if I turn around, we should be able to see another one. Whoa! There's a solar system map as well. That's a fun way for students to fly through and sort of see the distance between the planets relative to each other. Solar flares in this look really cool, right? They can also fly in them and sort of see what's going on. Here's Gliese. Teleport over here. So this is not literally Gliese, but it's what it would look like. So if you had a planet orbiting a sun, so you can see it's lit on just that one side, and then it's got this giant trail going on. So Chris did a really good job of illustrating this. You just have to have a really beefy, powerful computer. I'm on a desktop right now, so I can have like a real graphics card doing this. It's pretty hard to find a laptop that's good enough, especially if you're talking classroom sets of laptops, but pretty darn cool to see how that would look in this setting if you want to show that off on like a dome view or even just on a TV in the front and talk about it. The last item to cover is the last couple of days we give the students a chance to build together. This is when we've shown the highest rates of interest and learning. It's very cognizant in our cultural consciousness right now because of space travel, we're revisiting the moon, Elon Musk, all of this. they can go build a Mars habitat. And if you've been teaching it right and they've been going through the quest, they're thinking about habitation the whole time. Like that's a common theme throughout everything. So this is the presentation that I'm just going to walk through and how I explain it, but you could do it lots of different ways. We talk about how we've already started to explore Mars and the previous rovers that have happened. I like really hyping up the recent landing, Percy, because it had a heat shield, it had an umbrella with secret messages, it has a rocket-powered laser-guided backpack. That is a mouthful, and it is totally crazy that they have like the sky crane that lowers the robot onto the car-sized robot onto the planet that is now exploring around. The 2023 landing video is linked up there too. That's also fun. It's like the rover surrounded in a giant bouncy balls, and they drop in the lower gravity. But we can talk about how space exploration has changed some, that we have far more launches now. It's not just big governments that are doing it, and it's not just for research, and that there's hope for us to get to Mars in our lifetimes, or at least the kids' lifetimes, which is pretty cool. And we're probably going to see the moon. But there is this big important question that I ask them of like, why do you go to Mars? And have kids suggest different ideas. They usually come up with these 5. Sometimes they come up with permutations or additional ones. But curiosity and discovery, I want to emphasize that it's not just like finding life or because the Earth is going to die. Those are the 2 that I get the most often. But just this human achievement and also the kind of reality that we might be looking for resources in space. I mean, it's very expensive, but I would much rather us mine asteroids than destroy our planet. So, it's kind of a hopeful opportunity space. But we think about a secondary purpose of why exploration matters is that we develop technologies through doing this. When we went to the moon, we inadvertently, very purposefully, but we didn't set out to do it, developed all these other technologies that came out as a side effect of it. And I think there are more that are coming from space exploration now. I like that as a venue or vessel for technology development. Okay, and then we ask this question, what kinds of scientists and engineers do we need to live on Mars? Ultimately, we get to this idea of interdisciplinarity. I give some examples of kinds of roles, and we ask them who would they want to be in a Mars exploration, which is kind of fun. They can pick a role and decide what they would do, and they build out that part of the base. We contextualize this by saying that we're terraforming Mars, and so it's in the middle of that process. So stage 1 is sort of where we are now in real life, where we're just sending robots to scout it out and explore. We might have sent robots ahead of time with supplies or to start building a habitat component. We're in the build activity for the camp. We're in stage 2, where we're doing the first human habitations there. So they assemble a team, pick a role, and introduce themselves. And then we have this wonderful Kyrgyzstan video that explains all the challenges on Mars. And this is a great chance for them to learn about how they would build and want to build. So they do that for a day. And then what I would do actually after that first day is give some examples of real life Mars habitats. In 2017, NASA had a competition where people were invited to come up with designs. I start with this slide because every sci-fi movie and its mother depicts Mars like this, and it's a problem. They think there are these giant dust storms, and it's got a really thick atmosphere, and it's like, no, it's got like a light dusting of like razor-sharp electrostatic dust is what it really is. And it's just very low pressure. There's almost no atmosphere. So this idea of like tornadic winds on Mars is sort of a silly one that we see in movies. They got to create drama somehow. Anyway, Hassel, the architecture firm, was one of the competitors in that competition, and they came up with this idea of a shell that was printed by robots ahead of time that you then have inflatables, which is a really smart idea because they can fit really well on spaceships that have to go very far. And in some ways, an inflatable might be better than a solid thing. The walls might be just as tough or can self-heal and be made out of really cool materials. And this one also emphasizes redundancy. So just going back on the left here, there's like redundant airlocks for Mars or for spacesuits on the outside, as well as lots of systems. So if you lose a bubble, you can close it off and you have the others to fall back on. Neat ideas going on with this. They talk about how you don't have a lot of atmosphere outside, you have a lot of atmosphere inside. So it actually would crack apart the shell. So it's better to have the inflatable inside of the protective radiation shell. Here's our fleet of reconfigurable robots that would be helping to print the thing that would look like this before humans arrive. They were reliant on solar power. Here's another zoom in. A lot of the time the students are thinking things like, I'm going to build my room in the habitat. And rather than thinking about stuff like some of the other things you would want to do there, like having an engineering bay to repair stuff or a science lab to actually do research while you were there. But I love these because the Kyrgyzstan video is very accurate in saying that it's going to be basically a submarine cave. Is like our first habitat's going to be like that. And that's probably true. But if once our technology gets better and we have the ability to do things like build ahead of time, to land stuff like this is how it could look somewhat feasibly, where you could get light in, but you still have resistance from radiation. So that's a really nice, like, it doesn't necessarily have to be a terrible, terrible place to live. Apis Core has a series here too. We have all of these on our Mars map on the server. We'll go look at that briefly in a minute. But there are different visions of what this could look like. And these are just ways to think about different variables. Like you showing the examples, you can get talking about like, all right, where is basalt, which is a good material for making your 3D printed Mars habitats? Where can that be found? You could be deeper in Mars Veronera to the Mars Valley to be able to have more atmospheric protection from radiation. You can optimize for light, but also resist solar radiation. There's concern about, here's the sort of time lapse of how you might build the shells over time. Having shells, the coating where you have a layer of carbon frozen ice to protect from radiation on your habitable areas. This would be animated. It's that's a Mars quake simulation. And then finally, the one that won, Marcia, which I think is really the coolest. This idea of it's almost like a concave soda can. And inside of this, they have the stuff that's brought by the spaceship, but then they have the outer walls. And they actually built a 1/3 scale model of this in real life. They chose this shape because it's better at keeping air in. And you have the anti-gravity thing where you can walk upstairs every day to keep your muscles going. And they have this cool skylight that's got radiation shielding water. Then the light can penetrate all the floors to be able to get natural light going throughout the whole thing, which is helpful for a lot of reasons. And then here's that scale model there. They built like a 1/3 size version of it, which is pretty neat. And they had to think about stuff like how to fit the window in there and so on. And then this is not really relevant for this video, but we had a habitat assessor built on AI that looks at their block data and takes a picture of their base and can give them feedback on like what have they been doing well on for their habitat and not so well. And that goes with this little neat checklist. Let's see here. Here we go. We have these little quarter sheets that are given to each group. That you have them write down their team members and their habitat name, but also thinking about the challenges like atmosphere, radiation, health, power, all the stuff they have to build around. So it becomes this really good activity for them to go through building things to deal with all that stuff. You can also use this when at the end, the final day is we have them present their worlds, often to their parents, which is kind of fun. They can come in for that last day. And the team will talk about like the process of how it worked, and they can use this as a checklist of what to talk about. Because I think by default, kids will often be like, this is my bed and it's colored red. Like what they care about is often not as relevant to things like the science that they've been learning all week. So we have to sort of scaffold that process for them to think about it. Okay, let's go look at these in the game. So if you go visit Mars, you will get to just this sort of base version of the map. There's this little explorer here. These aren't actually full of anything. I think if I go in here, it's just going to be an empty, empty cylinder thing. There's not even stairs, really. I think it's the scale, and Minecraft doesn't really work very well for how those stairs would work. But we can at least see the habitats that I just showed you are present here. So if you want to walk their students through some examples, we've built those examples. This shell is actually really cool. It was actually made by this is the real 3D file from the Hassel people that I scaled down to fit on a Mars. And they've got some bubbles inside. These are ripe for like, you could copy this map and have students actually build in these to make the insides realistic. But they can also then build their own Mars habitat, either in this giant crater in a scale model, way scaled down because you wouldn't be able to see one from one end to the other of Mars Valley, or Olympus Mons, the tall volcano. They're typically building in the sides of cliffs, and so they can make these, make their habitats and sort of see some examples to inspire them for how to build them. But that's most of what I would say. Customize the habitat activity to the way you like. You also could do the same activity on exoplanets or on the moon. We just use Mars because you can check things like /atmosphere. We have it configured with science tools. Let's see here. It's 95% carbon dioxide. Telling us that. It doesn't. What that also doesn't tell us is /pressure. Not a lot of pressure. Um, so things like wind power, I'll often see students build turbines on Mars, which makes no sense. Are like they would want to do like a nuclear reactor or something. But anyway, they can build some really cool maps, and this is a great way to like cap out the week and where we've seen the greatest amount of interest in learning in our camps. That's all I've got for this video. Thank you for making it through this series. Hopefully you're able to run your own cool camps, or if you're a researcher watching this, you get a good sense of like what we do and how it works. Best of luck with astronomy education, and I hope WHIMC continues on for many years.